Hello everyone, welcome once again to CSE365. Slowly making our way through this semester. The end of the second module is very near for those unaware. It is due, let's refresh. It is due in 1 day, 11 hours and 56 minutes, aka it's due tomorrow night. I will once again highly encourage you to start and get all of your work ideally done before tomorrow night. Tomorrow night, the server, again, unfortunately, very likely, most of you will not listen to this message, and the server will be under heavy load. Now, I will be on standby watching the server, doing everything I can to keep it alive. Last time, I think we had like 10 minutes of downtime or something. But it'll be just like a little bit slower and laggier. It'll just be more frustrating. Do it tonight. It'll be great. I've been tracking the CPU usage of the server. This is like the last 5 days. So last night, people, there's a spike, and people tend to work at night. So, maybe if you can work during the afternoon also, that'll reduce some of your frustration. Again, even during these spikes, the server should realistically be usable, but I'm just telling you, you're saving yourself potential frustration if you avoid the very end. When we go above this red line, things become less ideal. So technically last night we went above the red line, but I don't think it was too bad. So on one hand, I'm telling you it's going to be fine, but on the other hand, I'm telling you there's potential for frustration. So take that mixed signal as you will. I'm going to try my best to make sure the server functions nicely, but I just highly encourage you to not work at the last possible moment to save yourself the potential for that frustration. Okay, so with that being said, the next module is launching soon, I guess according to the syllabus. Let's see. I think it launches right after? Course. Eventually. It will launch. Yeah, this is due tomorrow night, and then this will launch the next minute. So yeah, the third module will open up immediately after. And the third module, for those of you that are hating assembly, sorry, we're still sticking to assembly for a little bit longer. So highly encourage you to focus on this module and not get too lost, because some of this stuff does build on itself. Eventually, once we get off to like module 5 won't have anything to do with assembly. Cryptography won't have anything to do with assembly. Access control won't have anything to do with assembly. Web security won't have anything to do with security or assembly. Very last module, once again, assembly's back on the table. So even at the very end of this course, it's going to come back. So I encourage you to pay attention to what's going on in the module, because it will build on itself. And it will immediately build on itself in the next module, building a web server, where we kind of combine modules 1 and 2, where instead of being the client talking to some HTTP server, as you did in module 1, using Netcat, using curl, using Python requests, in module 3, you will be the server. You will be responding to web requests, as we will see, and you will do that by writing assembly to facilitate those requests. Maybe that sounds kind of spooky. I don't think it's too bad. You probably would rather write your web server in Python or Java or C or whatever language you like. I promise you it's not too bad to write it in assembly, and hopefully that'll just really drill in how assembly works, and more fundamentally, how syscalls work, which is what we're going to be discussing today. But before we do that, does anyone have any general questions about the class as a whole? Or anything like that? We're all on the same page? Nice. All right, well, you can always message on the Discord if any confusion shows up. Let's see, end is nigh. Cool. We will jump into or continue on from where we left off in the world of assembly. let's see here, refresh ourselves what we were doing. I think we were showing off that we can like call functions, right? We were calling foo, which was calling bar, which was calling baz. We had this whole stack being set up, this whole call chain. We were like persisting registers into memory. It was super cool. And before that, we did stir length. So we did this simple little algorithm to figure out how long a string is by just walking it byte by byte until we got to a null byte. Each time, each iteration through that loop, we were incrementing some register by 1 and returning the result. Now, something we've neglected this entire time is something like input and output. Like, how do I write a program? So, for example, one program that maybe is very familiar to you is the ls program. How the heck does this program produce output on my screen? Like, this is like a natural question. Like, the program's pretty useless if it can't take input or output, and all it can do is, I don't know, what you like assemble a program and have static data in it and it just runs through that. That'd be pretty boring. And so far, that's where we've been. In this class, we are going to be discussing how you get output, how you get input, how you get different things, how you start interacting with your environment. Because remember, even something like ls is just assembly. So bin ls, right? I don't think, well, yeah, we go to all these functions. We're not going to reverse ls right now, but you'll see there's a whole bunch of instructions. It's just x86. There's one special instruction that we have kind of ignored thus far, which is the instruction called syscall. And to demonstrate syscall, what I'm going to go ahead and do is we're going to wipe out this whole program and just go back to our boilerplate of Intel syntax no prefix, global start and start. This is where we're starting our very first instruction. And if we think all the way back to our very first example, where we made this program and it executed a single instruction, and we stepped, and we stepped, and we stepped one more time because GDB is weird and you got to step up bonus time for some reason, we get this segmentation fault. The program crashed. Okay, today we're going to finally make our program not crash. That's the first, probably the simplest syscall we can make is the syscall that says, my program's done. The syscall is known as exit. So the way we do that is actually pretty straightforward. So we previously talked about a thing called the calling convention, so that, if we want to call some function, everyone just agreed that the first argument goes into RDI, and the return value comes out in RAX. Everyone just agreed on that. Well, our code right now isn't just operating on the CPU. Our code is also, in the world of abstraction, operating on our operating system. And it turns out that the operating system is able to define a whole bunch of, maybe call it utility code. It's code for interacting, in a large sense, a huge part of it is interacting with hardware, but it also has to do with scheduling your process. How long is your process allowed to run before we temporarily pause it and then a different process runs? For those of you that have taken or are in CSE330 operating systems, this is the whole idea of the operating systems course at ASU, and probably every operating system course around the world. And so let's go ahead and demonstrate how that works. So you've written a program, probably in C, for example, that just did exit 0. Now, probably this is unconventional, because why would you do that when you could just return 0 instead? But maybe if you wanted to, check some ints argc, argv, right? We're checking our arguments, and then you say something like, if argc is less than 5, because you need 5 arguments passed, I'm gonna exit with exit code 1, and maybe I'll say puts usage program arg1, arg2, arg3, whatever, right? You create something like this, and then it allows you to early exit. And then if we didn't do that, we would call do work or something. This exit is ultimately making its way to a system call. This return 0 that's implicit there, but I'm going to put explicitly now, is also ultimately making its way to an exit system call. It's just main isn't calling the exit system call here. This cool function called libc start main, which calls main, is ultimately calling exit. If we want to do that just in vanilla assembly, the way we do that is we run syscall. There are a whole bunch of system calls, though. I'm going to tell you right now, for example, if you want to open a file, that is a system call. If you want to start a program, that is a system call. If you want to create another process, that is a system call. All of these actions that maybe you're kind of used to over the last few years of your CS career, of interacting with the environment in some way, doing all of these operations, these are all, or almost all of them, are system calls. It's a syscall. So I can't just say syscall. Somehow I have to say what system call I want to select. And this largely comes down to convention again. So the Linux kernel defines a whole bunch of system calls, and the specification says how you make a particular system call. If we look at man exit, so it turns out one of the system calls is exit. You might ask, how do we know all the system calls? We'll get to that in a second. I'm going to specifically do man to exit to see the system call variant of it. You're going to see something that looks like C, and that's because C is really close to assembly. So for explaining the calling convention and all the setup to it, it's kind of nice to just show C stuff also. We'll see that the function exit terminates the calling process immediately. Any open file descriptors, whatever the heck that is, we'll get there, belonging to the process are closed. Any children of the process are inherited by an it. Okay, the details of this are technical and important and correct, but we don't need to focus on it too much right now. Your instinct of exiting the program is probably correct. There's just some more details involved. The way that we specify which system call we want to perform, all of the system calls have a number associated with it. A nice resource for seeing what number goes to what system call is, and we have it linked in, do we have it linked in this? We might even have it linked here. No, but it will be linked in the next module where you will be doing a lot of system calls, is x64.syscall.sh. It's just a website that exists. Someone created it. And x64.syscall.sh tells us our system call numbers. So it says number, and here is a long list of system calls that Linux is providing to us. So we can see, over 300 system calls are available to do various operations. The first one we are going to look at is the exit system call. And this documentation says that it's 60. And it's 60 because Linux said the number is 60. And so makes this call number 60 if you want the exit system call. It's really as definitional as that. So the way that we specify our system call number is, again, by convention, we put into RAX the system call number. So we move RAX 60. And that means I'm getting ready. So similar to when we did a call to some function and we put something into RDI as our first argument. By convention, we put the number into RAX and then we perform the system call. And this transfers control. You can kind of think of this as just a jump instruction. It's a jump off to Linux kernel code. And Linux kernel code exists. It does a bunch of x86-64 itself. It does basically, if RAX is equal to 0, do this. If RAX is equal to 1, do this. If RAX is equal to 2, do this. And then eventually it says, if RAX is equal to 60, do this. And it's the exit logic. And then once it takes care of that, it returns. Now, in this case, this is a terminating syscall. There's no return, right? The whole idea of this system call is to exit. We'll see something like open returns because it's not a terminating system call. This one's a little special, there's nothing to come back to because we just said exit. And it's really that simple. So let's go ahead and run it. So we started by doing nothing. We did a NOP. Didn't need that, of course. We set RAX to 3C, hexadecimal for 60. And then we perform syscall. And you'll see that GDB reports to us interior 1 process 5169. So this is just like the process ID associated with this running program. It says exited normally. If I run it again, it exits. And it has a different process ID because every process has its own process ID. Turns out, I'm saying that, so I'll just point out, just to be very crystal clear, there's like lots of utility functions. So I said every process has a function ID. Well, guess what? There is a getPID function or system call. So PID meaning process ID. So if I do move RAX 39 and then do system call, let's see what happens. And we make this and we step. So we set up that we want to make hex 27 system call, aka get PID, by putting that in RAX. Again, just convention. There's no magic to this. It's just that's how it's defined. We run this. Now, we saw with function calls, like by normal cdecl calling convention, aka when we implemented that stir-length function, we decided to put the result into RAX. So the return value goes in RAX. That was the calling convention that we were using before, a very well standardized calling convention. It turns out that the Linux calling convention is almost identical with one weird dumb caveat, but we don't really care too much about that dumb caveat, to just the calling convention. The return value for this operation, because now we do have a return value, because it is returning, we're not doing the exit system call, is going to come into RAX. So right now, RAX is set to hex 27. If I step, and I'm going to step, the process ID for this current running program is going to appear into RAX. Before we do that, I can use GDB to run info proc. This will tell us some information about the current running process. GDB is very nice for doing stuff like that. We can see, for example, this is the current running program. This is our current working directory. And this is our process ID, 5673. So I am expecting to see 5673 appear in RAX after doing this system call. And specifically because, we're displaying this as hexadecimal, we're expecting to see that show up to us as hex 1629. So 1629 should appear in RAX if I'm not lying to you. And 1629 appears in RAX. So we successfully performed the get PID system call. You might think to yourself, this doesn't seem like all that useful of a system call. It's like this meta system call of like, what's our process ID? When do I ever care about my process ID? Fair enough, maybe you don't care. Of course, when I did info proc, if you think about it, GDB, somehow it got that this is the process ID. GDB under the hood performed that system call to figure that out at some point. And so we get our return value in RAX. Again, we continue executing. We now put 3C into RAX. We clobbered that return value because, this is how we wrote the program. And of course, as you expect, we exit. Now, I said that the calling convention is almost identical. And for our purposes right now, we'll just say it is identical to the cdecl calling convention. If I want to specify the first argument, who remembers from last week what the first argument is to a function? Does anyone remember what register we use for the first argument? No one remembers? Yeah, we've got an answer. Yeah. The what, sorry? So it like specifically what register? So for example, it could be RAX, RBX, RCX, RDX. Which one is the name of our register for the first argument? Just by convention. What is it? RAX. So it is not RAX. RAX is our return value, and in the world of syscalls, also our syscall selector. Does anyone? Yeah. RDX. You're close. It would almost feel more natural. It is RDI. So our very first argument goes into RDI. So I told you, I guess, last week that I showed these in order. So our very first argument goes into RDI. The second argument goes into RSI. The third argument goes into RDX. Yeah, there's a question. So this is where actually the cdecl calling convention differs from the Linux syscall calling convention. So the Linux syscall calling convention starts with RDI, then RSI, then RDX. Then it deviates from cdecl calling convention. So I guess I can show you very clearly what this calling convention is by writing a program. So if I do int foo, and I say int a, int b, int c, int d, int e, int f, our compiler here is going to follow this calling convention to produce this function. And I do foo, we'll just say return 0. We don't really care what this does. We're just trying to see the calling convention. And the compiler follows the calling convention. And we'll say 1, 2, 3, 4, 5, 6. So 6 arguments. After that, I think it's after 6 that it starts going to the stack. I don't know. I don't write programs that have more than 6 arguments. But of course, you could imagine a use case for that. If we go ahead and gcc test.c, call that test underscore c. We've got our semicolon. And we look at the obj dump of this. So we do this. We look at this. We go to main. We will see, so it does them kind of backwards, but fortunately we used a number. We'll see the first argument is RDI. Again, it's using the 32-bit version because we're using an int, and an int in C is a 32-bit value. If we use like a long or whatever, we'd use RDI. In fact, well, yeah, let's do that real quick just to make sure. Int, no more ints. We'll just say they're all longs now. I think that's going to give us what we want. Now if we do this, okay, well, we're going to ignore it for now. We're not going to go down that rabbit hole. We can see the first argument goes into RDI. The second argument goes into RSI. The third argument goes into RDX. Similar to what we're saying now, the Linux syscall convention is RDI, RSI, RDX. You don't have to memorize this. You can look it up every time. The more you do this, you'll just kind of get used to it. The next one, though, however, in the case of the syscall calling convention, it says it's R10. In the cdecl calling convention, it is not R10. It is RCX. And then they agree after that, R8, R9, R8, R9. So just to confuse you, because why not confuse you with two very popular calling conventions, the fourth argument differs in cdecl, so like C system, or the C calling convention, so like when you use the call instruction, versus the syscall Linux calling convention. Just this fourth argument is different. It'll mess you up at some point. And the reason for this is, I mean, the simple answer is because that's what the standard says, and they're both following slightly different standards because they can. The more correct answer, though, is if we look at the syscall instruction, there's kind of a weird little side effect of the syscall instruction that I didn't actually know about until like 3 months ago. So I finally figured out why we don't just use RCX, and for some reason this fourth argument is R10. And the answer has to do with the CPU itself. So RCX right here gets set to RIP. So this, we're clobbering RCX as part of the definition of how a syscall operates under the hood, like the microcode of the syscall, what it's actually doing. It affects RCX, and it sets it to RIP. And the reason it does this is actually kind of interesting. So when we were first introducing the call instruction, we started by using, I don't remember, I think we were using like RDX, maybe we even were using RCX, and we were setting whatever that register was to the next instruction we wanted to return to, we weren't using the stack, right? We were saving it off to a register. It turns out that the syscall interface, that's how it knows where to come back to. The syscall interface knows where to come back to because it puts where to come back to into RCX. So it changes RCX and then it comes back. And this works because syscalls can't be recursive. A syscall will never call a syscall, like under the hood. It's just one layer of syscalls, so we can clobber a register and not worry about recursion and arbitrary call depths. We save very efficiently. We don't have to access memory. Turns out accessing memory is a little bit slower than just putting it in a register. We put where we're going to return to into RCX. And so if that is a more satisfying answer to why the fourth argument is different, that is why. And actually, we could see when we ran this. Oops. What happened here? Oh, we didn't do this yet. We can see when we ran this, and I stepped, and you see when I execute syscall, so RCX is currently 0. If we step, we'll see that RCX is now the instruction we're executing. So we get to see the effect of that. The syscall instruction modifies RCX. That's another way that you could get bit by this, is if you go and make a syscall and you had some important data saved into RCX. I think this is how I originally found this, because I was using RCX to save some value that I wanted to refer to later, and then I made a system call. RCX gets clobbered by the syscall with the next instruction. So RCX is not safe going through a syscall. It will get modified. So that's kind of the technical reason why that fourth argument is different. Now you might say, why didn't CDecl just accept this and then they could have standardized? I don't know the full history. I'm guessing CDecl was first, and that's just where we are now. Okay, so that is calling convention. And so if we want to utilize that, it turns out that, for example, so you might say, well, how many arguments are to exit? Is there even arguments to exit? I just want to exit. Why would there be like a first parameter to exit? Well, we can look at man to exit to read the man page, and this will tell us that there is one parameter. It's the status. So the exit function can put a status in there, and that status, we're going to get into it. It has to do with a process hierarchy. So a process can start another process. So for example, our shell, when I type ls, our bash program is starting the ls program. And I can get the return value in bash by using this like $? thing. And this is going to tell me the return code of the previous program that exited. If instead I run the false program, we're going to see that $? does not return 0, it returns 1. So the convention for the exit system call, whenever you exit a program, if you exit with code 0, that means everything exited fine. If you exit with any other code, that means something went wrong. And again, this is also just by convention, how we do things. And different exit codes can mean different things. 0 just means success by convention. So I can specify what I want to return. So for example, if I put 42 in as my first argument, and I make this, and I step, and step, and step, and step, and step one more time, you'll see that GDB reports to us that inferior 1 process 10077 exited with code 052. Again, just to confuse you, because some of these tools just make interesting decisions. This is not 42, it says 52. The reason for that is this is octal. GDB decides that the exit code should be reported as octal, and that is what it shows to us. We can fix that for ourselves if we want. We can print it as decimal. And if we print decimal 052, the reason I know it's octal is because I've used GDB many times. And also, in general, if you start a number with like a extraneous 0, you just put like a 0 in the front, that often means octal. Similar to how 0x implies hexadecimal. So the return value is 42. Similarly, if I run tests, right, it doesn't really do anything that interestingly, except now because bash started test and test exited, which means bash now gets to see the exit code of test. We'll see that the exit code is 42. If I instead, of course, make this 33, we will see make test. What happened here? End of file. Oh, that's fine. If we run test now and look at the exit code, it's 33. So we're finally, now it's kind of boring for sure, right? Like we're just like returning an exit code. This is our first step into interacting with the environment. We're able to influence the bash program in some way by sending it an exit code of our program that just ran. Now, probably the obvious interaction with the environment that we all want to see, that we're all on the edge of our seats waiting to see, is how can I print something to the screen? So the way that we can do that is the write system call. So we'll see before the write system call is the read system call. We'll start with the write system call. You'll also probably see there's the open system call and the close system call. We're going to look at the write system call. If we want to print something out to the screen, the way that we do that is we use the write system call. So this takes 3 arguments, which means we're going to be filling in RDI, RSI, and RDX. It takes this thing called an FD. An FD is a file descriptor. Over the duration of this course, you will become very familiar. If you've never heard the term file descriptor, you will become very familiar with the term file descriptor. Then it takes a buffer as the second argument, and then it takes a count as the third argument. If we wanted to know for sure how the heck does write work, I would type man space 2 space write, and I would read this documentation, which similarly says FD buff counts, and it says write writes up to count bytes from the buffer starting at buff to the file referred to by the file descriptor FD, right? Very technical talk. What does that actually look like? So before we can understand what the heck that looks like, maybe we're kind of expecting what buff and count might look like, right? So count is going to be how many bytes are we writing somewhere. Buff is going to be what are the contents of that bytes. We're using memory for this. Remember, like if you think about it, you could imagine some implementation where instead of buff, we just put what we want to write straight into RSI, right? If we did that, we would be constrained to only writing up to 8 bytes because RSI can only hold 8 bytes worth of data. If we want to potentially be able to write thousands of bytes to the screen at once, I guess you could imagine doing 8 bytes at a time. Fine, you could do that. But if you kind of maybe think a little more practically, if you want to be able to write thousands of bytes at a time, as one probably might want to do, or more than 8 bytes at a time, we need to use memory. So we need to reference memory in some way. So similar to stir length, when we implemented that, stir length was looking at memory in some way and walking the bytes for a null byte. This is going to be similar. Count is going to be how many bytes we want to write. So this immediately we know because we're passing around a count. I previously said 2 common things are to null terminate your data or to pass around a size. This is using the pass around the size variety. And the reason for that is it's convenient in certain applications to be able to write out stuff like null bytes. And then we have whatever this file descriptor thing is. So a file descriptor, I think this is probably going to be the simplest way to understand a file descriptor. I currently have my bash program. So I'm using a shell right now. So if I clear this, my bash program that is running and allowing me to type commands is a process. It has a bunch of file descriptors currently associated with it. If I look at this, I'm using the ls program to list the contents of a directory. There's this fun directory called the proc directory, which allows you to introspect processes, self being my current process, fd being show me all my file descriptors. We will see, well, I guess there's more things than I expected, but I guess that's fine. Here's what some of these are, but we don't care. We will see that we have a bunch of numbers. So 0 points at dev pts 0. So dev pts 0 is some pseudo terminal. This is our terminal. It's pointing at a device that is our terminal. 1 is also pointing at that thing. 2 is also pointing at that thing. And then like 19 is pointing at this random log file, and 22 is pointing at this log file. This has to do with VS Code decided, I guess, to open up some files and point them at things because it's going to refer to them. Probably VS Code is logging stuff. And so that's why these file descriptors are open. The way that this works is if I ever write to dev pts0, dev pts0, this is maybe a little bit mind-boggling. Dev pts0 is a file, and it's a file that corresponds with like literally my screen. This file like somehow is my screen. Like this $ at some point was written to dev pts0. If you don't believe me, if I do echo test and we put that out to, let's say, hello, right? We've probably all seen something like this. I can say echo test, that appears on my screen. If I say echo test and I put that out to the test, oh, we won't do test. We'll say to hello, and then I cat hello, right? Test appears in hello. If instead I do echo test to dev pts0, this works. And what's going to happen? Well, it's actually not that interesting. It appears on our screen. The reason it appears on our screen is because we redirected where we're talking to back to where it initially by default is talking to dev pts0. This gets more interesting if I open up another terminal. If I open up another terminal, and let's see here, is there a way to do a split screen? Whoa, that's not what I want. Oh boy. Hold on. We want, why is this so difficult? Well, good enough. Okay. PS1 equals that. Clear. Okay. So I have two terminals open now. Turns out that if I have proc self fd1, I'm just going to show this one. This is pointing at dev pts0. If I do proc self fd1 for this guy, it's pointing at dev pts1. So there's two different pseudo terminals. If I echo hello, how is it going off to dev pts1, this appears on this screen. It really, this truly is the backing file for our terminal. Similarly, I could do echo it's going well off to dev pts0. And you could almost imagine having a terminal chat client where people are talking back and forth to their PTS files, and we have ourselves a chat room now. So if I want to print to the screen, the thing I want to print to the screen is dev pts0 if we mean this screen, or dev pts1 if we mean this screen. So we'll just keep it simple. We'll have one screen. And the way that we refer to the screen, this dev pts0 thing, is literally just by the number 1, or by the number 0, or by the number 2. Now there's a certain, I keep talking about conventions. We have all sorts of conventions. File descriptors 0, 1, and 2 all have a convention associated with it. File descriptor 0 is known as standard input. File descriptor 1 is known as standard output, and file descriptor 2 is known as standard error. And now all of these things are pointing at the same file, and that's because I send input, like my standard input, also goes to this magical file, this device file, and standard output also goes there. By convention, we specifically mean file descriptor 1 if we mean let's output to the screen. And so going all the way back to how do we write to the screen, we want to put a 1 in here as RDI because 1 points to standard out, and now it's all going to work. So what I want to do, we'll leave in our exit so that we can finally have a generic framework where we're no longer just crashing at the end. Kind of nice. If I want to do the right system call, my system call number is system call number 1. I'm going to put 1 into RAX. Then I need to set up my first argument. My first argument is this file descriptor. It is RDI. We need to fill in RDI with our file descriptor. We just said that is 1 because 1 means standard output. Now I need to specify some location in memory. This is what I'm going to be outputting. So for now, we'll say to do. We're about to deal with this because, for some reason, as soon as you start dealing with memory, it gets a little more, we got to think here for a second. And then how many bytes do we want to write out? Well, let's just kind of randomly say we want to write 10 bytes out. We'll have to figure out how many we want to write actually. And then we'll do syscall. So now all we're missing is whatever this to-do thing is. So we previously saw if we wanted to do str length, we set up some label. So for example, hello, and we did .string hello world. And this string is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 bytes. Now you saw me just do that by hand. You could imagine implementing a function like str length to do this 10-bit for you, right? I just did it by hand. Why do it by hand when you could let the computer figure it out? Well, because we're making it simpler, but we have a str length function that we could have called instead to determine what to put in here that would look for that null byte at the end and then fill this in, right? We would have called str length and then moved RAX into RDX. Now, we'd have to be careful about this RAX also, but hopefully you kind of understand the basic idea. And then similar to when we put offset hello into RDI when we called str length, because RDI is the first argument. Well, now we want this offset in RSI. So we put offset hello, and this, the linker is going to figure out where the heck this is, what the address is. It's going to fill it in for us. And we're going to get our reference to this piece of memory right here, now going in RSI. Let's make this. I feel like something didn't happen well. Make test. What happened there? Oh, doesn't like that still. Okay. Wait, why am I seeing? Oh, it's just scrolled down. Yeah, so we can see that we're about to load up all of these addresses. We can see that the linker figured this out for us, what the heck this address is, because we used a label and we set offset to the label. This value right here should contain our string, right? So this location in memory, again, if we print it as like, let's say 4 bytes, we would see hex 48, which is ASCII for H, uppercase H, then lowercase e, lowercase l, and so on. So if we continue along now and we step, so we're just setting up our registers here, and then we step again, and we step again. And now I'm realizing there might be an issue because of how we're visualizing things. I'm wondering where the heck it's going to go. But maybe it'll work for us. Otherwise, we'll run it without GDB. And I step one more time. Well, yeah, my fear is confirmed. The issue is every time I'm displaying this, I'm clearing the screen, so we lost the message. Let's run it without using GDB. But we saw the instructions are set up. And we run it. We will see we now get hello, comma, space, world, exclamation point, and then $ space. Why $ space? Well, because our shell is printing $ space before we're able to enter a command. If we wanted this like awkwardness to not be here, the solution is throw in a new line character. New line character means the terminal is going to deal with the new line character and go to the next line. And we increase this to 14. And we clear this, we make this. Oops, and we run test, and we get hello world, exclamation point, new line. Does anyone have any questions about this? About writing to the screen, about file descriptors, about buffers, about that count thing, anything to do with this? Because this is going to be the basic idea of just about every system call. There's one system call that we'll explore probably next class that gets a little weirder than a normal system call, but almost all of our system calls are going to look just like this. Okay, so I guess one thing I will point out is why do we have this like standard in, standard out, standard error thing? So I said one is standard out. Well, it's because this convention is very nice. When I run test and I do this greater than thing, This greater than thing in bash, what that means is just change where file descriptor 1 is pointing at before you run the program. That is the technical definition of the greater than symbol. So when I do /test greater than hello, it's not going to appear on the screen anymore because we're not writing to the screen. We're writing to file descriptor 1, wherever file descriptor 1 is pointing. It just happens that by default it's pointing at the screen. Here, now it's not on the screen. Instead, it's in hello. And it's in hello because before running the program, we changed file descriptor 1 to point at something else. That's all the greater than thing means in bash. And that's why we have this standardization and why this interface uses stuff like file descriptors. It's very nice because now you can run a program in a slightly different way and change the behavior instead of going to the screen to go to a file, etc. It's very flexible. If we want to do this kind of greater than logic ourselves, we can. We don't have to rely on bash doing this for us. If we specifically want to write to the hello file, right? We specifically want to write to ./hello, which is this file right here. We can do that. The way that we do that, by default, when we're running, we don't have any file descriptors open and pointing at hello. What we need to do is we need to use the open system call. So if you want to open a new file, you use the open system call. And we'll see here that that is system call number 2. It takes a file name. So this is our file name. That's going to be the path. It takes some flags. We'll see what those are. It takes this mode thing. We'll see what that is. And it opens it. So if we want to, instead of writing to file descriptor 1, right? We're writing to file descriptor 1 because we're putting 1 in RDI. What we need to do is we need to first open a new file. How do we open a new file? Well, we put into RAX the number 2, and then we syscall. So technically now we are opening something. What are we opening? Well, it depends whatever the heck is currently in RDI, RSI, and RDX. Probably nothing good. Probably this system call will fail. Actually, let's see this system call fail. The program will not crash doing this. The kernel will just say you're not doing something good. If we run this program and we step twice, we'll see what the heck ends up in RAX. Again, the return value always ends up in RAX. So we put 2 in, we do syscall, and this value that is FFFFFFF all the way to 2. This is a 2's complement number. This is, negative 14 or whatever the heck this is. That means some status code. It means something was bad, one of our arguments. We could look into what that error actually means. This corresponds to something. So we could figure out what it means if we wanted to. But we're not really surprised. We didn't set up RDI, RSI, or RDX with anything that means anything. In fact, right now they're all just 0. So we're kind of pointing at a null pointer for file name, and that fails. So if we want to open up, let's say, path string, and we'll say ./hello, or we could even just say hello.txt. Now this could be whatever path name you want. It's really not so strict. And this is going to be relative to our current working directory when we run this program. If we do this, now what we need to do is we need to load up RDI, our first argument, move RDI offset path, move RSI, flags, and then mode, whatever the heck these are. So we'll say to do. Okay, what the heck do we need to put in for flags? What the heck do we need to put in for mode? Again, you're going to get very comfortable doing this. Every time you have a question of how the heck does this system call work, you type man2 the syscall name, man2 open. This will tell us what all of this stuff means. The open system call opens the file specified by path name. If the specified file does not exist, it may optionally, if ocreate is specified in flags, be created by open. The return value of open is a file descriptor. So here's the file descriptor thing again. We just found out what's going to come back in RAX. So whatever comes back here, you better believe that we're able to now change out this file descriptor here from being 1 standard out to whatever the heck this returns to us. That's what's going to happen pretty soon here. And then blah, 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 blah. So the argument flags must include one of the following access modes: O read only, O write only, O read write. So you can open a file for reading, you can open a file for writing, or you can open a file for reading and writing. Now, this very clearly says that our flags thing is an integer. This thing right here is not an integer. This is O read only. How the heck do I put that in as my flag? Or O write only, or O read write? What the heck are these things? Again, this is a standard. These are constants. They have a definition behind them. It's just a number. In the same way that when I say pi, I mean 3.14, blah, blah, blah. This thing is just a constant. It has a number associated with it. There's various ways that you could figure out what the heck that constant is. My favorite thing for doing it is there is this user include directory, which has a whole bunch of header files. Somewhere in these header files is the number associated with it. So what I can do is I can grep user include for O read write. And specifically, I know it's going to look like pound define O read write. Oh, we did this backwards. I always do this one backwards. We put what we're going to search for, and then what we're going to search in. What? Oh, and then we also need a -r to recursively search it. And when searching through all of user include, we get the right header file. I guess it is the fcntl.h file that is nice enough to tell us what the heck the definition of this number is. I know this sounds almost insane. Like, why doesn't the man page tell us the number? It doesn't. It's very unfortunate, but O read write is just a number. Normally you're not writing assembly. Normally you're writing C and you're doing pound include. When you do pound include and you're able to refer to definitions, this is how. It's literally putting the definition of this in, and now you can just reference O read write. Well, we're not using C preprocessor or anything like that, so we need this number. We want to open this thing for reading and writing. We put that right here. So we want 2, because 2 means read write. I know it's weird. You're going to get very used to numbers just meaning things. And then RDX needs to get filled in with whatever the heck this mode thing is. So if we search for mode, what is this mode thing? Let's see. So we can, for example, open it in append mode. We can open it in whatever the heck async mode is, clo exec mode. We don't really care about this. O create. Let's see. I'm just searching real quick. Oh, and then it says the following symbolic constants are provided for mode. So this says 400, the user has read permission. 200, the user has write permission. 100, the user has execute permission. If I read through this more carefully, it's going to tell us that what the mode is it's specifically for if you open a file in a creation mode. If it has to create the file, when you create a file, your file needs permissions, right? We need to know, can user read, write, execute? Can group read, write, execute? Can other read, write, execute? Turns out, right, all of these files, if I look, for example, at hello, this right here, if you've ever paid attention to this bit right here, it says that the user or the owner of the file can read and write to it, the group can read to it, and other people can read to it. On the other hand, if I look at something like /flag, which remember, our goal is always to get /flag, only the owner can read it. Everyone else, the group can't read it, other people can't read it. And that's why it's permission denied when I cat flag, because only root can read this thing. So mode is when we create the file, what permissions are we giving to this file? We're not creating a file. We don't really care. Or we could show that maybe we are in a second. But for now, we're just going to say we don't care. We're putting a 0 in. Turns out it doesn't matter if we're not creating a file. We'll create the file externally. So I will do that, right? We're about to use hello.txt. So for now, I will create hello.txt myself. After this, we'll show that we can have automatically created it for ourselves. And then I'm going to make this program and we're going to run it. Looks like we're good to go almost, right? We're opening this file. So if I make test and I run test, it didn't do what I wanted. It didn't write this out to hello.txt. Didn't write it to hello.txt because I didn't tell it to write to hello.txt. All I did was open a file. There is a very cool program called strace that is going to show us all of our system calls that we make. And what you can do is you can do strace space /test, and it'll run the test program and show us every system call made. It's very convenient. So we'll see that we open hello.txt with O read write and a 3 comes out. This is the file descriptor now associated with hello.txt, and specifically this file descriptor means it's pointing at this path for reading and writing. And then we write to 1 hello world. It prints hello world. That's why it's kind of like awkward. We got this 14 business, and then we exit 0. So we wrote to 1. We didn't write to 3. If we want to write to hello.txt, we got to write to 3. That's what this file descriptor business is for. The result of this system call, as we said, all results go to RAX. The result is in RAX. So we need to somehow get the current state of RAX into RDI. Well, guess what? You can just do move RDI RAX. Is this going to work? Who raise your hand if you think this is going to work? Raise your hand if you don't think this is going to work. We got a few hands. People are unsure of whether or not it's going to work. Probably it's a leading question since I'm asking. This is not going to work. The reason it's not going to work is I put RAX into RDI, and then I put 1 into RDI. You're going to make these mistakes. You got to be able to read your code and reason about. This is where GDB comes in. Or actually, in this case, let's just make it and show that very directly it doesn't work. It doesn't work. We're not writing to the file. And if I strace it, strace./test, we'll see we open hello.txt, goes on file descriptor 3, then we're writing to 1. If we analyze this in our heads, we should be saying, okay, we open this file, it's going to file descriptor 3. The next thing we better see is that we're writing to file descriptor 3. And then I look back at my code and I say, what the heck? I put that in here. Why is it not writing to file descriptor 3? I took the result, put it in RDI. RDI is our second argument. Okay, you're going to make this mistake. We clobbered RDI. There's still a 1 in there. Get rid of the 1. Okay, we don't want to clobber it with 1. That's why it's 1. We make it again. We strace this thing again. Guess what? Now we're writing to file descriptor 3 very nicely. And also, you'll see it's not appearing on the screen. Oh, there's a question? Yeah. Yeah, so there's a question of explaining this offset thing, right? So this offset thing is not a CPU architecture thing. This is our assembler. So we're running this program called AS. And then also we're running this program called LD, right? When we do make test, well, I got to update it to see that. It's running AS test.s.-o, test.o, LD test.o-o, test. This offset thing has to do with the assembler and the linker. It's not a CPU instruction. We have these labels here, which means these are some bytes that need to end up in my ELF file at some point. These bytes, hello.txt, this dot string thing, this literally just means at this point in the file, put H, put E, put L, put L, put O, all the way followed by a null byte. Similarly with hello world. This path thing is a label saying, okay, so that's appearing somewhere in memory, some location into this file, and I want to be able to reference where that is. When I want to be able to reference where that is, that's where offset comes in. I can show you actually, if we do objdump-d mintel test, and we look at this, so it no longer says offset path, it just puts an address there. Okay, if I look at test.o, I believe, yeah, you'll see right here, it's just a 0. It's the LD program that's doing it. And I think if I do -dr, yeah, this thing right here, you'll see because I added this R thing, it's basically, it's not very readable until you know how to read it. This like extra line here is basically saying these 4 bytes right here, these literal 4 bytes, they need to be filled in with a value referring to whatever the heck we were referring to. Specifically, it's saying fill it in with whatever .text plus hex 48 is. So 48 being path. So LD, when it runs, it goes in and fills these 4 bytes in with wherever we resolve it to, right? Because right now, before we ran LD, start just has address 0. It's just offset 0 from the text section. Once we finally run LD and produce this test file, finally we have an address associated with it. And finally, LD can go in and fill in. So it actually fills in these 4 bytes of this instruction and puts the address there. This offset syntax just allows AS and LD to make that happen. You could imagine instead doing this without offset, and technically this will assemble. It just means something else. And maybe you're thinking this should do what offset does, and I probably would agree with you that we shouldn't need to specify offset. This is just because of how our assembler decides to do things. What this will do is, if we run it, it doesn't put in just that single value. Instead, you can see it says keyword pointer ds : this address. So it actually is putting in the address. So this address right here really does point to our path, right? hello.txt. But you'll see that it says keyword pointer. If we step through this, so if I step instruction and then step instruction, what just happened is RDI got filled in with this. So this right here. So it's not our address. We wanted 40104A to appear in RDI. Instead, this showed up in RDI. What the heck is this? Well, this is, if we print what's at this address, it's this thing. It actually dereferenced memory and pulled the contents out of memory and put that into RDI rather than putting the address into RDI. So that's kind of the distinction there. It's very subtle, but it's very different, right? And it just has to do with the syntax. The offset syntax makes sure that it's the actual address that ends there. If you don't do it, it decides, I mean, basically what it does by default is this, right? I agree probably with what you're thinking in your head that this should not be how this works. But that's just like a decision of the assembler producer that that's the x86 64 byte that they want to, bytecode that they want to emit. And so that's why we need this. It's unintuitive for sure, but that's how we do it. You might also commonly see something like this instead. Instead of move, we do load effective address. And I think I can even do it like that. Let's see. You might see this. And if we step, this is just another instruction. You'll see now we get what we want in RDI. It's more common when we're like trying to say, give me this pointer to use this LEA instruction, which means load effective address. Technically, does this also assemble? Let's see. Yeah, it does. It's the same thing. This works, and it's very common to use LEA in this way, technically. It's kind of actually less common to do move in this way. I just think it's conceptually simpler to just use a move because all we mean is move, but it requires this offset thing. Does that answer your question? Okay. So if we run this now and we rm hello.txt and we recreate hello.txt, and we run test, and now we cat hello.txt. Oh, it failed. So that's interesting. I didn't expect it to fail. So we're not seeing what we're expecting to see. One good way to figure out what the heck's going on is strace it. Well, it looks like so this is another way you would see it. Instead of using GDB, you can use strace. Strace is extremely, extremely nice when you want to see what's going on with your syscalls. It looks like our open succeeded. We got a 3. We got some file descriptor. Opened this path, opened it for read write. But then we decided to write to file descriptor 3 with this thing. Looks like I forgot to add one of my offsets back. And you'll see that it says -1 e-fault bad address. In other words, we could look into the documentation for what causes an e-fault, but we can see pretty clearly here, this isn't like a nice string like our previous string thing was. This is, we forgot our offset. So if I look at this, that looks correct. Maybe I just need to still make test. Yeah, I guess I forgot to make it. Now if we run it and cat hello.txt, did that work? It did. And again, strace /test. See, all of our syscalls succeeded. So GDB is a very, in some ways, difficult tool to use. I highly encourage you to try using it and get comfortable with it. Throughout this course, you will kind of be forced to become comfortable with it. I would say that strace is not a difficult tool to use. strace just literally logs all of your system calls to you, and it's very easy to spot issues, especially in this next module. This next module it revolves around making system calls. You should have a mental model of what your arguments to your system call you're expecting to be, and then just look at the log and see where it differs. I guarantee to you in this next module, if you're making a mistake, you're going to be able to spot which system call is messed up by looking at it through strace. And then you have to figure out, well, what the heck did I do wrong in my assembly that made that argument be wrong? But strace will be incredibly, incredibly, incredibly valuable to you for testing, making system calls. Does anyone have any questions about what we've been talking about here? Cool. Okay, so if we wanted to, I guess one more little example. If we wanted to have automatically created this hello.txt, we'll see that if I run it now, it fails. So because hello.txt doesn't exist, and I'm opening it for reading and writing, we're getting -1 back because it says no such file or directory. If we want to be able to also create the file, as the man page for open talks about with this O creates flag that for some reason is missing the last E at the end of the word create, it will create the file. So if I go ahead and do that grep little trick that we did before to find what the heck is O create, if I do look for O create within user include, we will see that the value is 01000 or 0100. Now I'm pretty sure, as I said before with GDB doing a leading 0 meaning octal, I'm pretty sure this is octal. And the way that it works for these flags is if I want to do O create and I want to do reading and writing, the way that you do that, so we said that the reading and writing was the number 2. So O read write is 2. And then I think this is about to be octal. Not totally sure on that. The way we specify octal in Python is 0O as the leading thing instead of 0x. We'll say O create equals that. Oops. If I want to do both of them, what that means is I do a bitwise OR. So O read write or O create. This means give me both of them. Or if we look at this, oops, did I? No. Or if we look at this, it's octal that, or if we look at this in hex, I don't know, whatever you prefer to look at this as. We'll just say 66. We're going to go ahead and put 66 in. Fortunately, strace for us will confirm that we're right because strace knows the values of all these constants and knows how to do all this bitwise OR as a display thing. Let's put 66 here. Let's make test, and then let's strace./test to see if we got this number right. Yeah, we got it right. So you see it doesn't tell us 66. It specifically says that it's smart. It's very smart, strace. It knows that this is read write ORed with O_create. And now we succeed because we said we're willing to create this file. One weird little thing now about this file, though, if we look at the permissions on it, the permissions are empty because that third argument is our mode. And we specified that our mode is, this is also an octal number. It's very common to do octal for file permissions. And I guess also ocreate definition. This is set up to, I mean, technically I think we can read it. No, we can't even read it. We could technically modify it since we own it, but even though we just created this file, we can't even read it because it is set up where no one can read this thing, no one can write to this thing, no one can execute this thing. There's a little weird caveat on why we were able to write to it. It's because we were also the creators. It doesn't really matter. If we want to make it so that everyone can read, write, execute this thing, what we would do is put 777 here. So if we do that, and we rm hello.txt, and we make test, and we strace./test, we'll see that we did octal 777. And now if we look at hello.txt, we will see, well, there's all these caveats. It doesn't matter for our purposes. Technically, it didn't end up as actually being 777 because there's this thing called the umask that also influences the mode. We're not going to go deep into that. But now everyone at least can read it. If we specifically wanted to say everyone can read it, we would have put 444. And the reason for that is this is octal. So this octal, this octal, this octal. This first one, number 4 means read, number 2 means write, and number 1 means execute. So 4 ORed with 2 would be 6, or 4 ORed with 2 ORed with 1 would be 7. And so we're only putting the 4s in, and so it's only going to be readable by everyone. So if we rm hello.txt, make test, strace test, lsl./test. Oh, well, we had, not test./hello.txt. We can see now it is readable by everyone. We're not going to go too deep into this read, write, execute. In fact, there's another module called the access control module. They'll kind of get more into this file permission stuff. Just know that it exists and it influences your access control permissions. That's how the flag works, is that only the owner can read from it. Again, though, we're not going to get too into access control at this particular moment. And it looks like we're also ahead of time. So thank you all for attending. Good luck finishing up this second module. Highly encourage you to finish today if you can. I know it's due tomorrow night, but try to finish today. Good luck and thank you all.